Good day, everyone. We are the Group 8. We are going to report about pumps. Firstly, the definition. Pump is a device that expends energy in order to raise, transport, or compress fluids. The earliest pumps were devices for raising water, such as the Persian and Roman water wheels, and the more sophisticated Archimedes screw. All pumps have an inlet, a casing, and an outlet. The inlet is where the liquid enters during operation. This is also called the suction side of the pump. Pressure is lowest at this point. Casing houses the internal parts of the pump and contains the liquid during operation. Outlet is where the liquid leaves the pump. This is also called the discharge side. Pressure is highest at this point. There are two types of pumps, dynamic and positive displacement pumps. Dynamic pumps impart velocity and pressure to the fluid as it moves past or through the pump impeller and subsequently convert some of that velocity into additional pressure. It is also called kinetic pumps. Dynamic pumps have two classifications, centrifugal and special dynamic pumps. Centrifugal pumps are rotating machines in which flow and pressure are generated dynamically. The energy changes occur by virtue of two main parts of the pump, the impeller and the volute or casing. This kind of pump produces an enhancement within force by transmitting mechanical power from the electrical motor to the liquid throughout the revolving impeller. The flow of liquid will enter the center of the impeller and exits along with its blades. Just like electrical fans, centrifugal pumps use motor to generate rotational energy to be used by the impeller to accelerate the fluid inside. The centrifugal power hereby enhances the velocity of the fluid and also the energy like kinetic can be altered to force. These types of pumps are the most used worldwide. The working is very simple, described well, and carefully tested. Whenever the pump is in action, then the fluid pressure will increase from the inlet of the pump to its outlet. The change of pressure will drive the liquid throughout the system. In general, centrifugal pumps are classified based on how fluid flow through the pump. First, axial flow pumps, also called propeller pumps. High flow, low pressure pumps which lift fluid in a direction parallel to the impeller shaft. Axial flow pumps have a motor-driven rotor that directs flow along a path parallel to the axis of the pump. The fluid thus travels in a relatively straight direction. These pumps are most often used as compressors in turbojet engines. Radial flow pumps are the opposite of axial flow pumps. They are high-pressure, low-flow pumps, which accelerate fluid along the impeller blades perpendicular to the shaft. The fluid handled leaves the impeller in a radial direction. The radial outward movement of the flow in the impeller causes higher centrifugal forces, which translate into higher discharge pressures, but typically smaller volume flow rates. They are commonly used for lift irrigation and drainage of agricultural lands, sewage applications, freshwater supply, and many more. Mixed flow pumps, part radial, part axial flow pumps. Medium flow, medium pressure pumps, which push fluid out away from the pump shaft and at an angle greater than 90 degrees. The main parts of the centrifugal pump. The wet end of the pump includes those parts that determine the hydraulic performance of the pump. The two primary wet ends are the impeller and casing. The mechanical end includes those parts that support the impeller within the casing. The mechanical end of the pump includes the pump shaft, sealing, bearings, and shaft sleeve. The impeller is a rotor used to increase the kinetic energy of the flow. It has three types. Open impeller. Open impellers have the vanes free on both ends. They are structurally weak. They are typically used in small diameter, inexpensive pumps and pumps handling suspended solids. Semi-open impeller. The vanes are free on one side and enclosed on the other. The shroud adds mechanical strength. They can be used in medium diameter pumps and with liquids containing small amounts of suspended solids. Closed impeller. The vanes are located between the two discs, all in a single casting. They are used in large pumps with high efficiencies and low required net positive suction head. The centrifugal pumps with closed impellers are the most widely used pumps, handling clear liquids. The impeller blades can be backward curved blade design, as shown in the diagram. It can also be radial blade design or forward curved blade design. Impellers can also be either single suction, which allows liquid to enter the center of the blades from only one direction, or double suction. This allows liquid to enter the center of the impeller from both sides simultaneously. Casing or volute. The casing contains the liquid and acts as a pressure containment vessel that directs the liquid flow in and out of the centrifugal pump. The volute is a curved funnel that increases in area as it approaches the discharge port. Shaft. The impeller is mounted on a shaft. A shaft is a mechanical component for transmitting torque from the motor to the impeller. Shaft sealing. Centrifugal pumps are provided with packing rings or mechanical seal. This helps prevent the leakage of the pumped liquid. Bearings. Bearings constrain the relative motion of the shaft and reduce friction between the rotating shaft and the stator. There are at least 5 common types of bearing, each of which operates on different principles: plain, rolling element, jewel, fluid, and magnetic bearing. There are several special types of dynamic pumps, which are defined by certain characteristics. Cantilever pumps are centrifugal pumps with long cantilever design used in some pump application. This is also called as vertical centrifugal pumps. Jet pumps are kinetic pumps with an ejector attached at the discharge outlet, utilizing the Venturi effect and motive fluid to generate pressure. Jet pumps are used in marine applications to transfer seawater. In home applications, they are used to move wastewater up to the sewer line. Turbine pumps. Centrifugal pumps that use pressure in combination with a rotary mechanism with numerous small impellers and vanes to transfer energy to a fluid. They are used in clean liquid applications that demand high head, low flow, compact design, and flexible operation. Horizontal centrifugal pumps. These types of pumps include a minimum of 2, otherwise more impellers. All the faces are in a similar shelter and mounted on a similar shaft. On a solo horizontal shaft, minimum of 8 otherwise additional stages can be mounted. These multi-stage centrifugal pumps are easier to install and maintain. The reason is this pump provides easy access to the internal parts. You can couple these pumps to an engine, electric motor, or even turbine. Submersible pumps. These pumps are also named as stormwater, sewage, and septic pumps. The applications of these pumps mainly include building services, domestic, industrial, commercial, rural, municipal, and rainwater recycle applications. Submersible pumps push fluid to the surface rather than jet pumps, which create a vacuum and rely upon atmospheric pressure. Fire hydrant systems. Fire hydrant pump systems are also named as hydrant boosters, fire pumps, and fire water pumps. These are high-force water pumps intended to enhance the capacity of firefighting of construction by increasing the force within the hydrant system. Hydrant service as mains is not sufficient. The applications of this system mainly include irrigation as well as water transfer.
Positive displacement pumps. Positive displacement pumps provide a constant flow at a fixed speed regardless of changes in pressure. The pump makes the fluid move by trapping a fixed amount and forcing the volume into the discharge pipe. The liquid flows into the pump as the cavity on the suction side opens or expands, whilst the liquid flows into the discharge as the cavity closes or decreases. Through every cycle of operation, the volume is the same. Positive displacement pumps are classified into two main types, which is the rotary and the reciprocating pumps. For rotary pumps are normally driven by electric motors, geared motors, or belt-driven with motors. Sometimes a rotary pump is driven by a steam turbine and in very rare cases by an internal combustion engine. It also has four main types, which is the gear pumps, the screw pumps, the rotary vane pumps, and the lobe pumps. For the gear pumps, these are a simple type of rotary pump where the liquid is pushed between two gears. These pumps are a kind of rotating positive dislocation pump, which means they force a stable amount of liquid for every revolution. Next is the screw pumps, which is the shape of internals of this pump is usually two screws turning against each other to pump the liquid. For the screw pumps, these type of pumps operate using counter-rotating screw rotors, which are engineered so that they would rotate towards each other. This traps the gas in the space between the screws of their rotors. As the screws rotate, this trap volume decreases, which not only compresses the gas, but it moves towards the exhaust. So for the next type of pump, we have the rotary vane pumps. These pumps are similar to scroll compressors. These have a cylindrical rotor encased in a similarly shaped housing. As the rotor orbits, the vanes trap the fluid between the rotor and the casing, drawing the fluid through the pump. The next is the lobe pumps. These pumps offer different characteristics like an excellent high efficiency, rust resistance, hygienic quantities, reliability, and etc. These pumps can handle high thickness fluids and solids without hurting them. So the next type of positive displacement pump is the reciprocating pumps. These pumps move the fluid using one or more oscillating pistons, plungers, or membranes, also known as diaphragm, while valves restrict fluid motion to the desired location. In order for the suction to take place, the pump must first pull the plunger in an outward motion to decrease pressure in the chamber. Once the plunger pushes back, it will increase the pressure chamber and the inward pressure of the plunger. Will then open the discharge valve and release the fluid into the delivery pipe at a high velocity. Typical reciprocating pumps are plunger pump, piston pump, and diaphragm pump. Okay. For the plunger pump, this pump is also known as a high viscosity pump or a high pressure pump because it provides a high pressure when it comes to pumping. These pumps can also pump both solid and viscous media. These reciprocating pumps is also used for pumping in industrial and municipal wastewater. Okay. For the next pumps, we have the piston pump. The piston pumps are the kind of positive dislocation pumps wherever the high force seal responds to the piston. These pumps are frequently used in motor irrigation, scenarios requiring high reliable pressure, and delivery systems for transferring chocolate, pastry, paint, and etc. The last is we have diaphragm pumps. The application of these pumps mainly include in continuous applications like in general plants, industrial, and mining. These pumps are particularly employed where power is not obtainable, otherwise in unstable and combustible regions. These pumps are also utilized for transferring chemicals, food manufacturing, underground coal mines, and etc. Okay, for the next slide, we have here the difference between a positive and non-positive displacement pump. So the positive displacement pump are those what I have discussed in the previous slides. So the examples of the positive displacement pumps are what I have mentioned earlier: the diaphragm pumps, the piston pumps, the lobe gear pumps, and there are also other examples such as the helical rotor and the peristaltic hose pumps. So for the non-positive displacement pump, to further discuss the definition, non-positive displacement pumps is the output flow rate that can change in response to the pressure on the outlet. They use Newton's first law of motion to move fluid against the system resistance. Although they provide smooth and continuous flows, their flow output is reduced as the system resistance is increased. So, a non-positive displacement pump's output flow changes in response to restriction on the outlet. This pump is used to circulate coolant around the engine block, or centrifugal pump used in an industrial plant to move fluid from one holding tank to another. This type of pump allows for slippage to take place inside the pump whenever the system pressure starts to increase. So, the examples of the non-positive displacement pumps are the centrifugal pumps, multi-stage pumps, and axial or propeller pumps. So here we have a table on what is the differences between the positive and non-positive displacement pumps, which is very self-explanatory considering that the table itself is already detailed. So for pressure, in positive displacement pumps, you have work in high pressure applications up to 800 bar. And for non-positive displacement pumps, the pressure is used for low pressure application, maximum pressure of 18 to 20 bar. For efficiency, the positive displacement pumps, the efficiency increases with increasing pressure. And for non-positive displacement pumps, efficiency peaks at best efficiency point at higher or lower pressure, and efficiency decreases. For viscosity, efficiency increases with increasing viscosity. And for the positive displacement pumps. And for the non-positive displacement pumps, efficiency decreases with increasing viscosity due to the frictional losses inside the pump. And for the performance, positive displacement pumps, flow is constant with changing pressure. And for non-positive displacement pumps, flow varies with changing pressure.
Pump components and seals. External and internal. The rotating seals are usually made of carbon, but they are also available in other materials such as Teflon, ceramic, and silicon carbide. And the stationary seats are usually stainless steel, ceramic, or silicon carbide. The rotating seal can be an internal seal, in which case it is inside the pump housing and submerged in the liquid, or external to the casing behind the pump head. The big advantage of the external seal is that there are lots of parts in the product area of the pump, and it is much easier to clean. The example shown for the external seal is a simple D-style single mechanical seal with a carbon seal which runs directly on the stainless steel back plate. There are upgrades to this, such as Type DG seal has a clamped in ceramic stationary seat. This long-lasting seal utilizes the standard D-type rotating components but has an added stationary seal of ceramic silicon carbide or tungsten carbide for other wear resistance. Type F seal has an added water cascade to clean and cool the seal. The flush helps to clean and cool the seal and will extend the life of the seal, especially in applications with high temperature and abrasive or sticky products. So next upgrade is Type E seal. It is a double mechanical seal with a full water flush. The seal assembly is complete encased in its own seal chamber and is flushed with pressured water. This seal is ideal for sluggish, heavy vacuum applications or extremely hot or tacky products. This would be a good seal for pumping maple syrup or honey, for instance. So here are the applications of pumps: pumping water from the wells, aquarium and pond filtering, water cooling and fuel injection in automobiles, pumping oil or gas and operating cooling towers in energy industry. They also have their uses in wastewater recycling, pulp and paper, chemistry industry, etc. Here are the common pump problems and solutions. First is little or no liquid delivery. So the solution of this is, if you experience a lack or loss of prime, fill the pump casing and suction pipe with liquid and check for leaks in suction pipe. Check for leaks in the mechanical seal and replace if needed. If pump primes well, shorten or enlarge suction line or lower suction lift. Check impeller and unclog, clean, repair or replace as needed. Make sure suction and discharge valves are open. Check suction screen and clean or replace as necessary. Check to make sure foot valve and check valve are not leaking and replace if defective. Next problem is suction is lost. The solution is check for air leak in suction line and repair or replace. Foot valve or strainer could be plugged or defective, unclog or replace. And if suction lift is too high, lower it, install foot valve and prime. Third common problem is motor overheats and or shuts off. The solution for this is make sure motor voltage matches power supply voltage and that electrical connections are tight. Impeller could be defective or rubbing against pump case. Clean or replace as necessary. And make sure wire sizing is correct and change if necessary. Next problem is pump will not start or run. The solution for this is first, check fuse or breaker and reset or replace as necessary. If any wires are loose or broken, tighten or replace. Remove anything blocking impeller. Replace motor if shorted out. Thermal overload. Allow pump to cool and determine reason for overheating before restarting. Wired improperly. Redo wiring. Fifth common pump problem is pump vibrates or makes unusual noise. The solution for this, tighten or reinforce as needed because pump may be coming loose from the mounting plate or foundation may not be sufficiently rigid. Impeller may be damaged and need replacing. Clean out any foreign material in pump. Motor bearings could be worn and need replacing. Suction lift might be too high. Lower lift and install a foot valve. Pump chart, also called a pump selection curve, pump efficiency curve, or pump performance curve. A pump curve chart gives you the information you need to determine a pump's ability to produce flow under the conditions that affect pump performance. Reading pump curves accurately helps you to choose the right pump based on application variables, such as head. Head is the height to which a pump can raise water straight up. Water creates pressure or resistance at predictable rates, so we can calculate head as the differential pressure that a pump has to overcome in order to raise the water. Common units are feet of head and pounds per square inch. A pump curve calculator might offer different units such as bar or meters of head. As figure 1 illustrates, every 2.31 feet of a head equals 1 per square inch. Flow, the volume of liquid you have to move in a given time period. As you will see, you can also use pumps in parallel to increase flow. This pump curve explanation also discusses variables such as pump speed in revolution per minute or RPM, impeller size as they related to pump performance, power, efficiency, net positive suction head, and centrifugal and positive displacement pumps. Reading centrifugal pump curves that contain additional information. Because some centrifugal pumps operate across a range of horsepower, their curves will include additional information. Figure 4, for example, features a pump that can operate from 2 to 10 horsepower depending on desired performance. Impeller trim size. Impeller size is another variable for meeting performance requirements. The curve from previous slide shows impeller trim sizes at the right end of each curve, ranging from a minimum of 4.33 inches to a maximum of 6.42 inches. Reducing impeller size enables you to limit the pump to specific performance requirements. The curve shows maximum pump performance with a full trim impeller, minimum pump performance with a minimum trim impeller, and the performance delivered by the designed trim impeller, or the impeller trim closest to the design condition. Impellers are typically trimmed 0.20 inches or 5 millimeters at a time. Impeller size is also a factor when handling shear-sensitive liquids or liquids that change viscosity when under pressure. Net positive suction head required or available. In addition to pressure and flow, the curve at the bottom of Figure 4 indicates NPSHR, which stands for net positive suction head required. So net positive suction head required is the minimum amount of pressure required on the suction side of the pump to avoid cavitation, or the introduction of air into the fluid stream. Net positive suction head required is determined by the pump. You always want net positive suction head available greater than net positive suction head required. NPSHA, with A standing for available, is determined by the process piping. Important factors affecting pump performance: surface roughness, internal clearances, mechanical losses such as those related to bearings, lip seals, mechanical seals, and packaging, high suction specific speed, impeller trim, and the viscosity of the fluid pump. Pumps are usually used to move liquid to a higher region, as liquid is pumped through the pipes and fittings. This friction will oppose the flow. This occurs from the walls of the pipe and disturbances to the flow path. This causes pressure drop in system, which wastes pump energy. The amount of friction depends on the liquid type as well as the materials and the fittings used. Therefore, it is necessary to consider and calculate how much friction or pressure loss the system will generate, and ensure that the pump selected can overcome these mechanical losses. Otherwise, liquid cannot be elevated to the other end. Major losses pipes encounter is due to friction in wall and is calculated by head loss is equal to the product of friction coefficient and pipe length times velocity divided by the product of two pipe diameter and acceleration due to gravity, known as the Darcy-Weisbach equation. That is the end of our topic. Thank you for listening.